Hello, good morning, everyone, and welcome to our Friday Happy Math Hour. Um, Again, if you're here to do Math 1314, please stay here. If you are here to do the Math 1324, you'll find a link on your chat. Go ahead and click on it, and you can switch over to your Math 1324 review. Okay? All right. Excellent. So, if everybody can hear me now, let's go ahead and get started, okay? So for today's Friday Happy Math Hour for our 1314, we're going to do standard form of quadratic equations and graphing. So let's first talk about what is a quadratic function. So a quadratic function, by the book definition, is any real numbers, and we have these very um, constants a, b, and c, okay, that relate to this quadratic function. Now, this quadratic function, the way you can recognize it is when we have a exponent of a 2 here, right? So the graph of all quadratic functions is this U-shaped graph, and we call this a parabola. Now here, f of x is equal to x squared is what's called our parent function, okay? So when we're looking at this, if you recall from chapter, I believe it was 1.7, uh, when we were dealing with polynomials, this is a degree 2 polynomial, right? Or also an even function, okay? All right, so the quadratic function in general form is like this. F of x is equal to ax squared plus bx plus c. And the standard form, which I hope you are familiar with it now because we saw it again in chapter 1, is in this form. F of x is equal to a x minus h squared plus k. And again, if you recall, h and k was the vertex of our parabola. Okay, so we're looking at these two graphs, f of x squared. Again, this is my parent, okay, my parent function here. And it's the vertex is at the origin 0 0, and again my parabola is pointing up. On this particular one, okay, when we see that we have a negative, this negative created a reflection on our x-axis of the parabola. It means that all our values are pointing are negative, so again our parabola is pointing down. Okay, all right, so here, again, just as I stated, when a is a positive number, when a is greater than 0, our parabola is going to open upward, okay? If a is less than 0 or negative, okay, our parabola is going to be pointing downward. And again, this a is both the a from our general form and from our standard form, okay? All right, so a little bit more features, okay? Now that we are dealing directly with a quadratic function, um, the book gives us better ways or easier ways with formulas to find some of this information. And one of the ways that in this new section helps us is to find the vertex using this formula down here. So to find the vertex of a quadratic formula is given by this. The x value, to find the x value of the vertex is going to be by getting negative b and dividing it over 2a. Okay. Once I have that value, I can plug it in back into the function and that will give me the y value. Okay. So let's go ahead and see more information. Okay. If you see here, when we dealt with quadratics in chapter 1, we know that they had y-axis symmetry, but now we can actually say that this y-axis symmetry can be represented as an imaginary line, okay? And we call this our axis of symmetry. Our axis of symmetry is the x value of the vertex, okay? So that would be our axis of symmetry. Again, our axis of symmetry, as just like the name sounds, it kind of like it's symmetric to the graph. It cuts our graph in half. Okay, I like to tell my students that the axis of symmetry is like a mirror. If I could put a mirror in and cut this graph in half, and the mirror reflects back my graph, then that is your axis of symmetry. Okay, so um, so it's convenient to convert from general form of a quadratic equation ax squared plus bx plus c into standard form, because if you see now that in this form here, it was very easy to say what our vertex was and what our graph looks like. In this notion here, if a is positive, all we can really tell that is our parabola is pointing upward. I like to also let the students know that in this format, they also give us the y-intercept. C will be your y-intercept always in the general form, okay? But it's especially convenient when we're sketching or graphing our parabolas, right? So let's go ahead and look at an example here. So to determine the vertex, again, this function is given to us in standard form. I can look at it and I can tell what our vertex is. Okay, so here in standard form, my h and k is given by these two values here. But I have to be careful because this is the formula. The formula says that the standard form is a times x minus h squared, okay, plus k. So if you see here, in my problem here, my vertex here was a positive one, but how did this plus um, became plus if the formula is saying it's negative? Well, this one had to be a negative one because a negative times a negative will be a positive. So hence, my vertex here is -1. But the 8k value here, okay, this one's positive and my formula has positive, so that value is just 12. So again, just by looking at the function in standard form, I'm able to see what the vertex is. Now, let's say that you forgot this formula here. What I also like to tell the students is think about you're finding the x-intercept of the graph. And if I wanted to find the x value and I have a +1, to move this one to the other side, I have to subtract one on both sides, which is going to give me that -1 value. Okay, so again, formulas are in this section are here to help us understand better quadratics. All right, so let's practice converting from general form into standard form. And this process is called completing the square. So we have this function here, f of x is equal to 4x squared plus 8x plus 16, and we want to write it in standard form. Okay, so the first thing we're going to do is we're going to group the x's together. Okay, not the constant. Okay, so here, if you see here, my function is 4x squared plus 8x plus 16. I'm gonna gather the ones that just have the x's. Okay, and we color coded them too, so you can see how the process is coming along. Okay, so once I separated this, what I'm gonna do is I'm just gonna factor the value. I don't want to factor the x's. I know that both of these two terms share an x, but I don't want to factor them out because then I'll lose the quadratic. Okay, I'm just going to factor the terms, okay? The coefficients, excuse me. So here, when I factor out the common term between these two coefficients, the common term is 4. So I'm going to factor out a 4. So what do I need to multiply to 4 to get back the 4x squared? Well, it's just the x squared. Here, um, I put it as a division, right? Because if I divide 8 by 4, it's going to give me the value that I need to have factored. Because again, if I say to myself, what do I need to multiply to 4 to get back an 8x? Well, that would be a 2x, right? So 4 times x squared is the 4x squared. 4 times the 2x is the 8x that I had before, okay? So now if you see here, this 4 is my a value, okay? So this is a good thing to see from our standard form, right? Now we have this middle part here. You see here we're missing the C part. So now is where we do the completing the square. Okay. So here the the steps to completing the square is given by this. I'm going to take the B value and I'm going to divide it by 2. I'm going to take half of 2. So 2 divided by 2 is 1. Okay. And then what that means is that when I square this 1 squared is 1. But what this means is this 1 is going to make this two terms a perfect square. And let me demonstrate what I mean by perfect square. So here I have x squared plus 2x plus 1 is my perfect square. But um, another thing that you're noticing here, I can't just add a 1 just because I feel like it. If I add something here, you see this is an equation. And by me adding a value, I would unbalance this equation. So I'll do a little bit of math manipulation, right? Because if I do plus 1 minus 1, the true value that I'm adding here is 0. I'm not changing anything. So I'm not unbalancing anything. So um, by me adding this plus 1 minus 1 is going to allow me to be able to add that 1 that I want. Okay. So what the next step that I'm going to do is here. I'm going to take this negative 1 outside the parentheses. And since I'm getting it outside the parentheses, I have to give back the 4 that I factored out originally that was inside the parentheses, right? So I'm going to multiply. 4 times negative 1 is a negative 4. Now that belongs outside the parentheses, okay? So if you see here, now I'm only left with what I wanted. I wanted this inside just to have x squared plus 2x plus 1, okay? And the reason why we wanted that is because what's inside these parentheses here is what's called a perfect square. Now, again, I clicked a little bit too fast, but here, I didn't tell you that I had a plus 16 already outside, and I had that minus 4 that came from taking the negative 1 outside. I'm going to combine these two like terms. A positive 16 minus 4 is the 12, and this is where I'm getting the 12 from, okay? All right, so now I'm here, and the reason why I wanted that 1 here is because this becomes what's called a perfect square. This is the same thing as x plus 1 times x plus 1. That's what the square means, that I have two terms that are identical that are being multiplied with each other. And again, if I would do to FOIL, when I multiply x times x, that gives me the x squared. X times 1 is the x, 1 times x is x plus x is 2x, and 1 times 1 is 1. See? So I can rewrite this perfect term in this format. 4 times x plus 1 squared plus 12, and lo and behold, we converted from general form to standard form, okay, where we have a is our value for 4, and we have our h and k. Now we know that our vertex is at negative 1, 12, okay? So again, this is a great way for us to be able to sketch terms if they're giving us the function in um, standard form. So let's go ahead and practice some more determining, converting from general to standard, so we can graph and find our vertex. Okay. So again, um, first of all, let's just review here. We have this x squared plus 2x plus 1. Okay. I'm going to complete the square again. So I'm going to make a little space here because I need to add the c here from the x squared and the 2x. Do you see here, my a was 1, so there was nothing for me to factor. So in my future standard form, my a is going to be 1. Okay. So again, I'm going to do the process. I'm going to take half of b, or in this case is 2. 2 divided by 2 is 1. Okay. Square 1, that's 1. So I'm going to add 1 minus 1 because I can't unbalance that equation. I'm going to take this negative 1 outside the parentheses. There's nothing for me to give it back because I didn't take it out anything. I didn't factor out anything. So it just becomes a minus 1 outside. Okay, so I'm left with x squared plus 2x plus 1 inside the parentheses. But outside, I'm going to go ahead and combine my like terms. A positive 1 with a minus 1, that's 0. So that just leaves me with this x squared plus 2x plus 1. But again, I know that's a perfect square. It's x plus 1 times x plus 1. I can rewrite it as x plus 1 squared. So now I have converted it from general to standard. And I know that um, my my vertex is at negative 1. Again, um, this plus 1 came from 1 being a negative 1. And since there's no k value, that value is 0. So my vertex is at negative 1, 0. And again, to review, the axis of symmetry is always the x value of the vertex. So my axis of symmetry, or the equation of my axis of symmetry, is x equals negative 1. Okay. All right. So if we continue. Let's try it one more time. Let's practice converting from general form to standard form. So I have this function 2x squared plus 8x plus 7. The first thing that I'm going to do is I'm going to put a parentheses between the two terms that have an x, and I'll leave the constant term outside. Okay, I left a little blank because I know that I'm missing the c part. But before I do the c part, I'm going to factor out a term from these two. Okay, I always want this one inside to be 1. Okay, so we always want to do this. So here, the common term that I can factor between 2 and 8 is a 2. So I'll factor out a 2, and it's going to leave me with x squared plus 4x inside. Okay? So now again, I'm going to complete the square. I'm going to take b. b is 4. Divide by 2. Gives me 2. I'm going to square that value. 2 squared is 4. So I want this to be a 4 for this to be a perfect square. So what I'm going to do is I'm going to add 4, subtract 4. Again, never want to unbalance my equation because I'm really adding 0. I'm not adding anything to it. Okay, so I'm gonna borrow that positive 4. I'm gonna put it in parentheses. I'm gonna take the negative 4 out, but by me taking the negative 4 out of the protection of the parentheses, I'm gonna give back the 2 that I factored out. So 2 times a negative 4 is a negative 8. Okay, so I had a positive 7 outside. Let's combine those two like terms. Negative 8 plus 7 is a negative 1. And now I know that x squared plus 4x plus 4 is a perfect square. X plus 2 times x plus 2. But you hear me say, oh, I already know that this is x plus 2 times x plus 2. And I tell my students say, well, Mr. How do you know that is x plus 2 times x plus 2? Very easy. What I do is I say, okay, what is the number that 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 I had when I got this b value and took half of it? What was that value? Well, that value was 2, right? So that's what's telling me that it's 2 here. How do I know that it's x plus 2 and x plus 2? Well, it's the sign of the b value. Since the sign of the b value is a positive, that means that both of them have to be positive. So x plus 2 times x plus 2 gives me this perfect square. Okay, so again, this I can rewrite as x plus 2 squared, and I am done. I converted this function from general form into standard form. And it's now, with what I know that this vertex is at negative 2, negative 1. The axis of symmetry, the equation is x equals negative 2. Again, it's the x value of the vertex. Okay. All right, let's try it one more time. So I have this function in general form, 5x squared plus 15x minus 5. Let's do it, okay? First, I am going to put parentheses between the two terms that have an x, okay? And then if this term has anything other than a 1, I'm going to factor it out. So I'm going to factor out the 5. So it's going to leave me with 5 times x squared plus 3x. Now let's complete the square. Let's take half of 3, which is going to be 3 halves. Again, this is the term that's going to give me the perfect square. This is the value that I'm going to look at when I make my perfect square, okay? So I'm going to square that. So 3 squared is 9. 2 squared is 4. So I have a ninth fourth. So I want to have a 9/4 there. So I'm going to add 9/4 and subtract 9/4, okay? So I'm going to borrow the positive 9/4, close it, take the negative 9/4 outside the parentheses. So that means I have to give back the 5. So 5 times a negative 9 is a negative 45 over 4. Yes? So I'm going to combine my like terms. To add these two, I need to make 5 into a fraction so I can add them, because to add fractions, I need a common denominator. So originally I had 5 over 1, but to make 1 into a 4, I need to multiply by 4. So 4 times 1 is a 4. 4 times 5 is the 20. So now I can add them. Negative 20 minus 45 is a minus 65 over 4. Yes? So again, here, again, if you remember what I told you, before I got the square, the value was 3 halves. So that's what makes my perfect square. I have the 3 halves, and since b had a positive sign, both of them are positive. So x plus 3 halves times x plus 3 halves gives me my perfect square of x plus 3 halves squared. Okay, so now I know what my My vertex is a negative 3 halves and a negative 65 over 4. The equation of the axis of symmetry is x equals negative 3 halves, the x value of the vertex. Okay, all right. So now, now that we have our quadratic in standard form, we are able to look at our graph and also go backwards, right? If they give me the graph, I can get this in standard form. So if I see this graph, okay, I'm always thinking of my parent function. Originally, my parent function had a vertex at the origin at 0, 0, but this graph, I look at it, it got shifted 1 unit to the left and 1 unit down. This is my h and k value, right? So those are two terms that I already have. This is the standard form. A is equal to x minus h squared plus k, where the vertex is hk. So I have that, but in order to come up with the standard form, I'm going to need an additional point. And since this parabola, excuse me, crossed through the origin, I have another point. And again, this is your homework. Your homework is always going to give you 2 points in order to be able to do this, to be able to look at the graph and get the equation of that in standard form. Okay, so let's go ahead and do it. Let's plug in what I have on what I know. Okay, so I knew my h and k. Again, my h was -1, my k is -1. I'm going to plug it into the formula. Okay, so my h is here is -1, my k is -1. Okay, and I also know a point. I know the x value is a 0 and my y value is a 0. So when I evaluate this, okay, I'm going to be able to solve for a, my only unknown. So here we have a negative with a negative is a positive, but 0 plus 1 is just 1. 1 squared is 1, so that's giving me a. A minus 1, to solve for a, I'm going to add 1 on both sides, so a is equal to 1. So now I have everything to write my standard form. Again, a is 1. My h was, again, the -1. My k is -1. So based on this graph, the standard form of this graph, or the equation of this graph, is f of x is equal to x plus 1 squared minus 1. Okay. All right. What if they don't give us a graph, but they give us the 2 points? No problem, right? So they're giving us what we need. They're giving us the vertex, and they're giving us another point on the graph. Okay. Now on this one is nice because they're basically giving me the y-intercept, right? If we recall from chapter 1, when x is equal to 0, we get our y-intercept. But let's go ahead and do the same process that we did right now. Okay, I know the equation of the standard form of a quadratic is this. Okay, they're giving me the h and k, and they're also giving me an x and y value. So the only unknown that I need to solve for is my a um, variable. Yes, so let's go ahead and solve. So we, again, f of x replaces the y value. So this is 3. We don't know a yet. Okay, our h is a -3. Our k is a -15. So let's do the process again. We simplify. A negative with a negative is the positive. 0 plus 3 is 3. 3 squared is 9. Um, and then we have 3 is equal to 9a, or a 9 minus 15. Again, I want to isolate the a, so the first thing I'm going to do is I'm going to add 15 on both sides. So 15 plus 3 is 18. Now I'm going to divide both sides by 9. So 18 divided by 9 is 2. 9 divided by 9 is 1. So a is equal to 2. So the equation in standard form, based on these 2 points, is f of x is equal to 2 x plus 3 squared minus 15. Okay. All right. So here, just to review, to find the x-intercepts, we let y equal to 0. But one of the things that you're going to see in this new chapter, they're not going to tell you sometimes the x-intercepts. Sometimes they're going to tell you find the zeros of the graph, or find the zeros of the quadratic, or the roots of the quadratic, or find the solutions of the quadratic. All these four things mean the same thing. X-intercepts, zeros, roots, and solutions are all talking about the same thing. where the graph crosses the x-axis, okay? Again, our x-intercepts. So let's look at this, okay? So there's many ways to solving quadratic equations or to find the x-intercepts. So one of them is the square root property, but as you may know, sometimes we can't use this or it's not always useful because we can't set it up to be able to solve for the square root property. Now, my method of choice is factoring, but sometimes we cannot factor or the or the equation is not factorable, so we cannot always rely on factoring. But I liked it because it's the easiest. But that's just me. Um, but the for sure way that will always work is called the quadratic formula. Okay. Now, um, keep in mind that if we move our graph up above the x-axis and our a is positive, this is telling us that um, our parabola may not cross the x-axis, hence it may not have any solutions or it may not have any x-intercepts, okay? So, and algebraically, we're going to find out when that happens, okay? And you're going to see it. So let's go ahead and practice some of these methods. So let's first demonstrate the square root property if it's possible. So in here in example one, it says solve f of x. And again, when they're asking us to solve, they're asking us to really find the x-intercepts, right? So for this first one, I'm going to set y equals to 0. And here you see that I can't do my square root property because I'm able to solve for the x. So the first thing that I'm going to do is I'm going to add 4 on both sides. And I'm going to get 4 is equal to x squared. Now I'm going to take the square root of both sides. Okay, so when I take the square root of both sides here, um, the square root is the inverse of a square. But if we do this algebraically, we multiply a 1/2 exponent times 2, which is 1. I know you all like to say that they cancel, but they don't really cancel. They just become the exponent becomes 1. Okay, so here x becomes 1, but I know what the square root of 4 is. The square root of 4 is plus or minus 2. So I have two solutions or two roots or two x-intercepts for this first example. X equals 2 and x equals negative 2. These are the two places where my parabola crosses the x-axis. Okay. So let's look at the second example. I have f of x is equal to 3 times x minus 4 squared minus 27. So I'm going to do it the same way. I'm going to set y equals to 0 and I'm going to solve for x. The first thing that I need to do is I'm going to add 27 on both sides. Okay, so this is going to give me 27 is equal to 3 times x minus 4 squared. This 3 is being multiplied to this, so I'm going to do the opposite. I'm going to divide both sides by 3. So 27 divided by 3 is 9. 3 divided by 3 is 1. Okay. The next thing I'm going to do is I'm going to take the square root of both sides. Okay. So I have the square root of 9 with the square root of x minus 4 squared. Again, I lose the square because the exponent becomes 1. So on the right side, I just have x minus 4 left. And the square root of 9 is plus or minus 3. So now the last thing I need to do is add 4 on both sides. Excuse me. So when I add 4 to the plus or minus 3, so if 3 was positive, I have 4 plus 3 is 7. If 3 was negative, I have 4 minus 3, which is 1. So my two solutions for this quadratic is at x equals 7 and at x equals 1. And again, the solutions means that these are the 2 points where my graph crosses the x-axis, the intercepts. All right, so and again, I have a picture here on this one to demonstrate what we just solved. We solved where the parabola here crossed our axis at 1 and at 7. Okay. All right, so another way we can solve quadratic equations is factoring. So let's say that I have this function x squared minus x minus 6. I'm going to do again, set it equal to 0, but this time I'm going to factor. And the way I like to factor is, again, we did a class. Mr. Isasi gave us a great presentation on how to factor these trinomials. Okay, so I like to say I want to find two terms that when I multiply them together give me negative 6, and when I add them together give me a negative 1. Well, what are those two terms? Negative 6 with a positive 1. Negative 6 times a positive 1 gives me negative 6, and negative 6 plus 1 gives me um, Sorry, no, no, not negative 6 and 1. Um, I can't do that one. It's negative 3 and negative 3 and a positive 2. Excuse me. And negative 3 times 2 is give me a negative 6, and negative 3 plus 2 is give me the negative 1. So here I have a product that should equal to 0. Okay, so the only way that these two can equal to 0 is if either of these two x values gives me 0. So if we don't see it, we can separate them. We can say what x value gives us 0 when I have x minus 3, and what is the x value that when I add it to 2 will give me 0. So here we see that if x is equal to 3, 3 minus 3 will be 0. So that's one of my solutions. And here, if x is equal to negative 2 plus 2 would also give me 0. So again, doing factoring will help me solve this quadratic. Okay? All right. So then the last method, the one that always works, is what's called the quadratic formula. The quadratic formula is given by this one here, which is states. Um, Given an equation in general form, which is like the one we have here, we can get negative b plus or minus the square root of b squared minus 4ac all over 2a. Again, just to recall our general form, okay? Our general form here in this particular function, a is 1, the b is a negative 2, and the c is, and all I have to do now is plug it in, okay? So So let's go ahead and plug it in, okay? Um, and let's simplify. So here, a negative times a negative is a positive 2. Inside the radical, negative 2 squared is 4. And then we have a negative 4 times a 1 is a negative 4. A negative 4 times a negative 8, a negative times a negative is a positive, and 4 times 8 is 32. Okay, and then 2 times 1 is 2. Let's continue simplifying. Let's simplify inside the radical. The 4 plus 32 is going to give me 36. So I have 2 plus or minus the square root of 36 over 2. So the square root of 36 I know is plus or minus 6. Okay, so here, when we do the 2 plus or minus 6, I can have um, 2 plus 6 is going to give me 8, and then I'm going to divide by 2, and then I have the 2 minus 6 is going to give me 4, and then I'm going to divide by 2. So let's see here. So, ah, what happened here? Give me 1 second to think this is. Oh, I see what we did. Okay, so what we did was we did the plus or minus 6 divided by the 2 first. So we had plus 6 divided by 2 is 3, and no, but still, I think there's a typo here. Let's go ahead and see if we can fix this. Okay, so we have this. So let me go ahead and I don't think this is it. Let's do this. So we have 2 plus 6 divided by 2. Okay, so 2 plus 6 is 8 divided by 2 equals 4. Okay, there we go. Um, I wasn't understanding this line. Okay, so here's one of our x values, x equals 4. Okay, let's do this again. 2 minus 6 divided by 2. Okay, 2 minus 6 is a negative 4 over 2, and negative 4 divided by 2 is negative 2. Okay, so I'm not sure where we're getting the 3 from, so that's why I did it again. So here are two solutions which are correct here. X equals 4 and equals negative 2. Okay, all right, let's move on to section 2.2. So graphs of polynomial functions. What is a polynomial function? So here, if we're talking about graphs of polynomials, we were taught that is any graph that has smooth curves and that I can graph the graph without lifting my pencil. If I can do both of those things, then um, this graph is a polynomial. So a graph of polynomial does not have breaks like this example here. There's a break here. It's here, then it stops, and then there's point does not exist, and then it continues. So a polynomial function is a function that has a continuous graph, and that's what it means that I don't lift up my pencil, and it doesn't have any sharp turns, okay, and it doesn't have any breaks, okay. So that's visually what a polynomial function is. So again, continuing with what I had just mentioned, this this graph on the left is a polynomial. It has smooth curves. Okay, it's continuous. I'm not lifting on my pencil. Doesn't have any breaks, and it doesn't have any sharp turns. So this first one is a graph of a polynomial. But if I look at this next one, I know that this is a an absolute value graph, but this is not a polynomial because again, this has a sharp turn. This is what I mean about a sharp turn. It's like um, there's basically um, a 90-degree turn, right? There's not a curve. It's not a smooth curve. Okay. All right. So to be able to graph and polynomials that basically don't have parents, okay, we're gonna apply something that's called our leading coefficient test. That's gonna help us determine what a graph's end behavior looks like to help us graph any polynomial. Um, of any degree. So, but to do that, I'm going to use two parent functions that we have been dealing with. Okay. So if you see the first two graphs are graphs of parabolas. Okay. So these two graphs are quadratic graphs, or they come from this first one, my parent function f of x squared, and this is the one with the reflection of the negative x squared, right? If you recall, these other two graphs are my cubic functions. Okay. They look like kind of like an S. Okay, this is my parent function x cubed, and then when negative x cubed, since this is an odd function, it has a reflection on the y-axis, and it's looking at the other side, right? So I'm going to use these two parent functions to explain the leading coefficient test. So let's start with the quadratic. So my quadratic is an even function. And the reason why I know that this is an even function is I like to tell my students, I look at the exponent. Since the exponent here, or the degree of this polynomial is 2, and 2 is an even number, this makes the quadratic an even function. Okay? So now that I know that this is an even function, what I do is I ask this, okay? If my leading coefficient here, and the leading coefficient is the value that is being multiplied to the term that has the highest exponent. Okay, the degree is 2. This is the the leading coefficient is the value associated to the degree. Okay, so since here this value I know it's 1, but what I'm more interested in if that value is either positive or negative. Since this value is positive, the end behavior of this graph is this way. This is how you would answer your homework. The end behavior is rises on the right and rises on the left. Okay, this is what it means. That the end behavior, the endpoints of this graph are pointing forever up and pointing forever on the left and pointing forever up on the right. If my leading coefficient of an even function is negative, then the end behavior is this way. It's going to fall on the left and fall on the right. Okay? Thank you, Ms. Chuka. All right. So if you are dealing with a polynomial that is an even polynomial or a degree of even number, if it's positive, rises on left, rises on right. If it's negative, the leading coefficient is negative, fall on left, fall on right. Now let's look at the odd. Okay, this is an odd polynomial because again, my degree here is 3. 3 is an odd number. So this is an odd polynomial. Okay, so here, if we see, if my leading coefficient is positive, the end behavior for an odd function that has a positive leading coefficient is going to rise on the right and fall on the left. Okay, if my polynomial is odd, but my leading coefficient is negative, okay, the end behavior is going to rise on the left and fall on the right. Okay, so this is how we can help us graph any polynomial. So let's look at some examples. So let's look at these, and let's start first on describing the left-hand and right-hand behavior, or again, the end behavior of these functions. So let's start with A. So the first thing that I need to see is find the degree of this function or polynomial. So again, the degree is the highest exponent that the terms have. So if I see here on this A, my first one, the degree is 8. Okay, you see it's our highest exponent. So now I ask myself, 8, is that an even number or an odd number? Oh, that's an even number. So then that means that this polynomial is an even function. Now I have to look at the leading coefficient of this polynomial, which is a value of 3. But again, I'm not interested in right now that value. I'm only interested in the sign. This 3 is a positive. So then that means that I'm dealing with an even polynomial with an even or with a positive leading coefficient. So the end behavior for A is going to be rises on the uh, left and rises on the right. Okay, it's this one right here, right? Even function, positive leading coefficient. So end behavior rises on right, rises on left. Okay, let's look at B. Okay, um, B is in the degree is 3. That's the highest exponent. So the degree of this polynomial is 3. 3 is an odd number. So the leading coefficient here is negative. So the end behavior for this one is this one, right? It's an odd polynomial, odd function. Since the leading coefficient is negative, it's going to rise on the left, fall on the right. Okay. How about C? We got to be careful, right? Usually the leading coefficient is the first one, but the homework is going to try to trick you. If you see here, my highest exponent is 8 over here, right? So this polynomial here, the highest is 8. So um, it's an even function. So, but the leading coefficient here is -4. Um, we could have done 6. 6 is an even function, but we would have gotten the leading coefficient wrong because the leading coefficient is not 1, but -4. So again, so since this is an even function and my leading coefficient is negative, it's going to fall on the left, fall on the right. It's going to give me this graph right here. Okay. All right, let's do this last one, D. Okay. This -2 got factored out, so we got to pay attention to that, okay? But let's look at the exponents. The degree, the highest exponent that we have here is 3. So that's my degree 3, okay? So I am dealing with an odd function. But I need to, this value is not 1. They factor out a -2. So if I give this back, if I factor back in this -2, the coefficient of this leading coefficient is a -2, hence it's negative, right? So I'm going to have an odd function with a leading coefficient of a -2. So the end behavior of this is going to rise on the left, fall on the right, okay? So again, this information as far as knowing what the degree of the polynomial is and what the leading coefficient will let us know the end behavior. And this is going to allow us to be able to graph any polynomial function. So for instance, to continue reviewing and helping us being able to graph, there's another thing that I want to point out. Okay, when a graph crosses the x-axis, okay, we know that those are their solutions or the roots or the x-intercepts of the graph. But these points here, when the graph touches and turns back, those are also called intercepts. Okay, the fact that they touch the x-axis are still considered solutions of our points. But when they touch, what they tell us is that they are a double zero. Okay, anytime that a graph touches the graph and comes back, it means that we have multiple zeros. Okay, so for instance, in this first middle one, we see that our graph touch that -2, right? Ms. Chuka, thank you. So here, if we see the solutions here, we have x equals -2, x equals 2, and equals -2. We have two um, solutions where our x value is -2. And our graph told us that because it touched. If we looked at this third example here, we have this W looking graph, but here you see that the graph touched the graph and then turn around. This value here is the origin and are at 0. So in this graph, we all see two solutions where x is equal to 0. Okay, so again, this is another piece of information to help us graph. Okay. So let's look at this. So knowing this, we go to this topic of called multiplicity of zeros. So the multiplicity of zeros will determine whether a graph crossed the x-axis or it just touched and turned around. Okay, so let's go through some of these processes. When we have zeros, where we had zeros equal to x squared, again, originally you thought, hey, the quadratic should have two x-intercepts, but when it's the parent function, there's only one at 0. But no, now you know that this 0 was a double zero, okay? Because when we took the square root of 0, yes, it gave a 0, but it was two zeros. And one of the ways that I also like to tell the students is that um, this 0 is from the one where the graph is decreasing. That's one of the zeros, and also it's a 0 from when the graph becomes increasing, but it's two zeros. So the multiplicity for this one, again, we would say is 2, okay? So, and again, we see it because the graph touched stuff and then turned around, okay? It didn't cross it. If we look at this one here, again, our cubic function, 0 is equal to x cubed, we can rewrite this as x times x times x, right? Any of these could be zeros, so we have three instances of zeros. So our multiplicity of zeros for this particular example would be 3, okay? So this is what we're talking about when we have an odd multiplicity or an even multiplicity. The number of zeros that have, if it's an even number, it's called an even multiplicity. And if it's an odd number of zeros, then it's an odd multiplicity. Okay. All right. So let's look at this example. Find all the real zeros and determine the multiplicity of each zero. So we have f of x is equal to x squared minus 2x plus 1. All right. So the first thing that I want to do is let's find the x-intercepts by using the quadratic method. Okay. So um, or any of the quadratic mixes. So it looks like we're going to do factoring. Okay, so I want to find two numbers that when I multiply them together give me 1, and when I add those same two numbers give me -2. Well, those two numbers are -1 and -1, right? -1 times a -1 is a +1, and -1 plus a -1 is a -2. So this guy factors in this way. 0 is equal to x minus 1 times x minus 1, right? So you see here, I have two instances of x, so when I solve them, they give me the same value. X is equal to 1, right? So then this means that this is an even multiplicity because I have two x-intercepts. But what is it telling me about the graph? That at this point 1, this graph touched the x-axis and turned around. Okay, so basically it's a parabola that just moved 1 unit to the right. Yes? So again, if I look at my graph, again, and I'm always thinking of my parent function. My parent function originally was at origin at 0, but this graph got shifted 1 unit to the right. See, it touched that 1 and then turned around. Again, this was, we're at 1, it occurred twice, so this is an even multiplicity. Yes? Let's look at this one. Find all the zeros and determine the multiplicity of each zero. Okay, so here we have f of x is equal, or actually this should be t, right? F of t equals to t to the fourth minus t cubed minus 30t squared. Okay, so first I'm going to set it equal to 0 and use any of our quadratic methods. Okay, so I set the function equal to 0. And then the first thing that I'm going to do is I'm going to factor out a t squared. Since I see that this, they all have a t and the smallest exponent is 2, I can factor that out. So I have t squared is equal to, or excuse me, t squared times t squared minus t minus 30. Okay, so now let me factor this inside. That one I'm going to factor out by doing this. -6 with a +5 gives me the -30. a negative 6 plus 5 gives me the negative 1. So this is what I have. So if you see here, now I'm going to have three values for t, right? So I have um, um, 0 is equal to t squared, 0 is equal to t minus 6, 0 is equal to t plus 5. But this first one here, I take the square root of both sides. So this is a double 0 right here, right? This 0 here, it counts twice. This is a individual 0 because if I put 6 here, 6 minus 6 will give me 0, so that's 1. And then this one here is another just 1. So when t is equal to negative 5 plus 5 is equal to 0. Okay, so again, the 0 here has a two instances, so it's an even multiplicity, right? And then at 6 is just only 1, so that's an odd multiplicity. At negative 5, there's only 1, so that's an odd number, so that's an odd multiplicity, okay? So again, this is the way we can find out the multiplicity of our zeros, okay? How many times they appear as solutions, okay? All right, now moving on, why are we doing all this? Well, we do all this so we can be able to graph something that might not that be easy to graph. So let's write down what we have, okay? So I know that I have some solutions, right? I have some values of t where it crossed the x-axis, okay? At negative 5, I know at 0, it was a double multiplicity. The graph touched and came down. And then at positive 6 here, yes? So what we can do is um, find values. Oh, well, actually, we're not going to do that yet. Let's do another one. Okay, but let me go back to this one, what I was going to get to. Again, my points here, we can't see them because they're outside the graph. But if we really wanted to find out what these values are, we can just pick random values between these intervals to get a better sense of the graph. But I think we're going to do that at the end. Let's practice more trying to sketch. So let's look at this problem here. This function g of x is equal to x cubed minus 3x squared. The first thing I'm going to do is I'm going to set it equal to 0 and then solve it. But let's go through the process to sketch this graph. I'm going to find the end behavior, find the zeros, which is what I was going to do already. Find any intercepts, the y-intercepts, since the zeros are the x-intercepts, I don't specify it. And then I'm going to plot additional points, which is what I was talking about earlier. Okay, so let's go ahead and do this. Let's do this problem. So first I see that the degree of this polynomial is 3, so that's an odd polynomial, and the leading coefficient is 1, so that's a positive. So I know that the behavior will rise to the right and fall on the left. Okay, that's one thing. Let's find the zeros. Again, I'm going to set it equal to 0. I'm going to factor out an x squared, and I'm going to get here, this 0 is going to have a multiplicity of 2, which is an even. This x is equal to 3. That was only one instance of that, so that's an odd multiplicity. So again, I know that at 0, the graph will touch and turn around. At 3, it's actually going to cross it. It's going to intersect it, yes? Okay, so let's find the y-intercept. To find the y-intercept, to review, we set x equal to 0. So 0 cubed is 0, negative 3 times 0 squared is 0, so 0 plus or 0 minus 0 is just 0. So my y-intercept is at 0, 0. Okay, so let's put what we have. We know that the graph touches and turns at 0, and we know that it crosses it at 3. We also know that this graph is going to fall on the left and rise on the right. So let's go ahead and put those arrows here. On the left of this 0, it's going to fall. And to the right of this 3, it's going to rise. Okay, this is the end behavior of this graph. But then we don't know what's happening in between here. This is where we want to put some additional points. So some additional points to plot. In this case, I just picked 1 and 2 and 2.5. And the way that I chose these is, again, I picked values that are between these 2 points. Okay, so that's why I picked the 1 and 2. And since these values here probably have another curve going on here. That's why I picked the 2.5 to get a better sense of what's happening here. How far is this graph going down, right? So if you see here, when I plugged in 1, I got a y value of -2. When I plugged in 2, I got a y value of -4. And when I put in my calculator 2.5, I got a y value of -3.125. So let me go ahead and more or less estimate where those points are, and I have something similar like this. Now again, you will be plotting on WebAssign, which is the computer. The computer does all this nice graph for you. But again, this gives you a good idea of what the graph should look like. And again, this is what the computer is going to do, not my version, which is a little scribbly, right? So again, but again, this helped me be able to get this graph that is aided by the computer. Okay, so again, I'd like to thank you all of you for joining us today for our Happy Math Hour review. What we did this week, which we started the quadratic functions. Again, I will pass it now to our presenters. Thank you again for joining us.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind all of you our previously recorded sessions were all available on the YouTube playlist. Today's session will also be available on the playlist later on today. Also linked is a short survey to help us improve our TV sessions, so please take the time to fill out the survey. We will be back with a Happy Math Hour next week, where the Math 1314 will cover synthetic division and complex numbers. And Math 1324 will be covering solving exponential and logarithmic equations. Before you leave, I want to share that today's TV sessions we will have at 1 p.m. The student success topic today will be the Writing Center and CSD. Thank you all for coming in today. We hope that you all have a lovely weekend. If you have any questions, feel free to use the chat box or mic at this moment. Have a great weekend, guys.